Welcome to the HiRSE-Seminar series on research software engineering in Helmholtz and beyond.
Yeah, thanks very much for the kind introduction, Claire. As you said, we will talk about our work on retrieval augmented generation, which is a very nice technique that allows integrating private data and basically private data into AI solutions like chatbots or LLMs. We structured our talk into five parts, five main parts, starting with the introduction and motivation, like why is it all needed? What is so nice about it? Which problems does it solve or address? Then I will hand over to Mascha. She will talk about the fundamentals and give an architectural overview of how rack systems are typically designed. Then coming to a part where Victor will tell about how to integrate data, because this is like the main challenge, how to get your raw content into your AI solutions. Then Mascha will take over again, talking about something that may be very interesting for you, software engineering people, how to integrate this into practical applications. And I will conclude with a summary, strategic takeaways, and next steps for you. Yeah. So starting with the introduction, right now you only see me, but with me are my two very nice colleagues, Mascha and Victor. We are, as Claire said, in a group called Applied Machine Learning here at the Jülich Supercomputing Center at JSC. We grew quite drastically and are now already more than 20 members in this group, and it's led by Stefan Kesselheim. This is our group leader. To show some of our activities, so this is not a complete list, but some related activities, I put those here on the slide. And maybe most important is Mascha and Victor are working on application development and spent now more than half a year on building rack solutions, exploring rack solutions. And the maybe other interesting part is AI consulting. This is where I'm mainly involved in that we offer our consulting services to you, to the whole community, and can help you build those kind of applications. So to motivate this talk, let's start with a problem statement. And this is an example use case we took at the beginning of this project. We thought about, okay, what kind of documentation or documents do we have here internally? And there's this HPC user documentation here in Jülich for the JSC systems. And we played around with it a bit. So in this screenshot, you can see that there's quite a lot of content on the left side. You see all the pages. And there's a traditional search engine. So if I, for example, search for what is the maximum runtime for GPU jobs, and I already typed it in precise keywords as you would do in a Google search, you see that the search results are somehow excessive. You don't really see here in the overview if those pages really answer your question, if it's relevant or not. And it would be nice to somehow enhance this and have a maybe better workflow where you can even type in natural language. You don't need to care about precise keyword matching, but it's about semantic understanding. And this is where you may think about, are maybe LLMs a good alternative as a search engine? And in this screenshot, we show our experimental LLM hosting service called Blablador, which is also operated here in our group, and it offers the use of open source large language models like Llama 3.3 in this example here, and in natural language. I mean, probably you all have experimented with LLMs. If I ask here, what is the maximum runtime for GPU jobs on Joules at JSC, I get a very long answer. It looks nice. It is written in natural language, but there's a problem with this because just to point out some parts here, the answer says, for example, there is a standard or default partition and a long partition, and those just don't exist. So you have the problem that the LLM kind of gives an answer that looks nice, but it has no access to the domain-specific data here. And there's not really a guarantee that this answer is correct. So yeah, main problem here, hallucination in this case. So this is our proposed solution, which we frame for the moment as something like an AI-powered search engine. And here in this experimental application, so I quickly want to highlight the disclaimer. This is something experimental. We're just trying with it. That's no production ready product. But it enables to ask questions like, what is the maximum runtime for GPU jobs in natural language? And we get a single AI summary answer. And this is not only an LLM answer, but it has access to the search results that are displayed below. So it takes this question, does information retrieval, so it retrieves those chunks of answer. We will get back to that in the following slides, how that works in detail. And then combines those search results with the power of an LLM to generate a nice answer. And this is correct now. We have the partitions GPUs and booster named, which are indeed partitions available on our systems. Yeah. So this is motivation. And now let's see how we got there. And I will hand over to Mascha, who will talk about the fundamentals and architectural overview.
Thank you very much for the introduction. As I said before, I will now go over to talk a bit about the fundamentals of RAG and give an overview of when it's actually applicable and what prerequisites you actually need. Afterwards, I will give a bit of a theoretical insight into the actual core components of RAG before my colleague Victor will actually go into the details that are important for the implementations. RAG is primarily used to overcome a specific problem with AI chatbots, that they have no access to up-to-date data or, of course, our internal documents. Typical sources for this are, for example, really like articles from the internet that was just recently published or documents that have unpublished data from our organization or even personal information. While we do have, like in ChatGPT or Microsoft Copilot, some solutions to integrate documents and web search, we cannot risk like putting our sensitive information in there, and as such, these solutions are not always available for us. This is where actually the RAG application comes in place. RAG is able to like link to a web data or, more importantly, the internal data sources, and then create a pipeline to give this data to, for example, a secure AI application that we ourselves have set up. In a traditional chatbot, that would be, for example, just piping through the chunks and then generating a natural language answer. It is to note here that while RAG is a wonderful solution for this problem, we still are dealing with AI. That means we can miss information, and AI might try to integrate its world knowledge into the natural language answer. But at the end of the talk, I will actually give a short overview over some techniques where we can minimize these effects. But now enough from the use cases, let's get over to the prerequisites. So what do I need if I want to test or build a RAG application? So most important it is to get access to a so-called embedding model. For now, it is only important to notice that this is like the core of the RAG, which will transform the text in something the machine can work with on a semantic level. Good for us is that a lot of embedding models have been pre-trained and are available to different frameworks, as for example the Ollama framework that you can run locally on a computer or a local server setup, and the application you just saw, BlaBlaDoor, also offers a rather safe API. Additionally to this core element, we would recommend looking into the LangChain Python package, because here, most of the core elements of RAG, like in a preview, chunking, embedding, etc., are already pre-implemented. So what kind of hardware do you need to run this? your personal laptop is enough for first tests. The size of the hard drive really only depends on how many documents you have. So if you say you just have some papers lying, unpublished papers or manuscripts lying on your PC that you want to test with, you don't need any kind of extra hardware, and just 2 CPU cores are absolutely fine. The prerequisites only are high if you decide to host an embedding model yourself. Then you will have to look in the prerequisites of this model itself, and most likely, if you want to use it productive, will have to invest into GPUs. The expertise is also rather low. You need to know a bit about how to use an LLM, on the level of the interface or the API configurations. A spoiler, 3 lines of code normally. And only when you really want to go into things like prompt engineering and fine-tuning the model behind it, more specific knowledge is needed. But absolutely not for getting a start into RAG. So we hear RAG pretty often right now, but what is actually hiding behind this word? Behind these words are actually hiding 3 steps: the retrieval, the augmentation of the retrieved data, and then the generation of a natural language answer. Let's start with the first step, the retrieval. In this core step of the RAG, you can read in your private documents in the before mentioned embedding model, and the embedding model will create more or less a semantic database, here called vectorized data, but often also called vector store. When you do the same with the user query, you have data and the query in the same semantic space, and the RAG chain is able to more or less facilitate an AI-powered search. To understand this better, let's have a look at a simplified example. Let's, for example, imagine that our document is just a list of words. Normally, this list would be a list of longer paragraphs. But for here, just say we have barking, dog 4, car, motorcycle, and apple. The embedding model, using its word knowledge, that's important that this model is a pre-trained model and not just the raw structure, to translate these words into a string of numbers. These number strings represent vectors, which then are sorted into a semantic space. This sorting happens when indexing this data into the vector store. On the right side, you can see a very simplified display of a vector store. Normally, it's very high dimensional. Here we are just looking at a hypothetical example with 2 dimensions. You notice immediately that the words form group in this vector representation. In the upper left corner, you have fur, barking, and dog. Then in the lower right corner, you have car and motorcycle, which are definitely unrelated to the upper. And the apple, which relates to none of both groups, stands a bit alone in the right upper corner. So now the question remains, how does that now helps us to get away from this not so efficient keyword search into the more efficient AI search? The magic behind this is that we use the same embedding model with the same word knowledge to also embed our query. Let's imagine that we want to fetch every word that is semantically related to the dog. We can more or less imagine this, that the vector store now tries to match the query to the most closest thing it has in its database, or even makes a new point. Here, of course, the dog, and then it tries in a parameter to search for this, search for all the close neighbors, which in this example are fur and barking, but not apple, car, or motorcycle. This, of course, in the RAG application normally happens with larger text parts like multiple sentences. The output here are normally the semantically close chunks, here from here on called the retrieved information or the retrieved chunks. while this is the functional core of RAG, normal applications go further with the augmentation and generation step. In the augmentation step, the retrieved information and the original user query are put together in the simplest version, just a query and then the information, and then piped into a large language model. In the step of generation, the large language model then hopefully tries to use the received information to actually answer the questions and then give us a natural language question. In the next section of the talk, my colleague Victor will now give you a detailed look inside how to prepare and integrate actual real-world data to be applicable to this data chain.
Okay, so as Mascha said, I will now talk about data integration and like globally all the RAG system, especially the retrieval part, because it is the most important part of retrieval augmented generation. Sorry. So I divided it into three main parts. So parsing, splitting, and encoding. And let's dive into this. Let's first talk about parsing. So the idea of parsing is to transform your data into AI readable text. It is really important and it has to be considered during your RAG journey. So here is a PDF about my imaginary dog, Sir Barks-a-Lot III. It contains specific information that an LLM cannot answer on its own. For example, the first paragraph of my document explained that my dog can speak 3 languages, English, Spanish, and French. You can see that this PDF contains various types of data. So there is like some written text and also some tables. I mean, one table and one image. So I also want you to notice that we have a really clear structure with some headers that we can notice as human because of the larger font policy, sorry. And all of this information are really important to keep and to bring to the LLM. But why can't we give just the PDF to LLM or embedding model? We can do this because most models do not have any native multimodal support, meaning that primarily process text and cannot directly interpret images for mating and other visual elements. So we have to extract this content of our document into a list of tokens or written text, basically. However, this is really challenging because we need this information. We need to keep the structure of our document because the LLM will need it to really understand the document and being able to generate the right answer for your question. So it is really challenging. Before going to the next slide, I just want to tell you that there is 2 main Python libraries that can do RAG. That can help you to do RAG, so long chain and llama index. And for the next presentation, we will, so as I explained, this document is our example, and we will use like long chain tools to do the RAG. Llama index offer the same tools that I will present with long chain. You can use your favorite Python library. Wait, okay, sorry. So what is basically long chain offers a lot of different loaders that you can use for free. I will use for this example the most basic one for PDFs. So it is PyPDF loader from Longchain. And the idea is that on the left you have the PDF and on the right you have the written text extracted from the loader. I would like to focus on a lot of part because as you can see there are a lot of defaults. In red you can see the headers. Here we lost the structure of the document. The headers are just like common text and have the same font size. In blue, you can see also the table. As for the headers, we lose the structure of the table, losing the delimitation lines. In green, you have the picture. Here, we lost all the content of the picture. So we lost a lot of information. And in purple, you have like, you can see it on the PDF, but it is the number of the page. So PyPDF loader will just extract all the written context without any filtering. And that is a real problem. I would like to tell you that LangChain offers a lot of different loaders, and I would recommend to try all the potential loaders that could fit with your data, because it will save a lot of time if you find one that is working. But you have to be ready to potentially build your own strategy, because sometimes your data are too complex to use a basic loader, and you will have to pay more attention to this stuff. Now we'll talk about splitting. So why do we need to do splitting? LLMs have like a limited context window. It means that they can't take more than a number of words of tokens as input. So most of the time, I believe that your data will be longer than this limit. And then we have to find a solution. The solution is splitting, of course. There are many methods that can be used to split your data. I won't talk about all of them, but I will talk about 3 popular methods. So the first one is the fixed length method. The idea is to select a length, so it can be a number of tokens or a number of characters, and split your text into chunks of the selected size. This method has some good points and bad points. I would say that it's really nice because it doesn't require anything. You just need written text, so you can always use it. And the other good point is that you will have always same size chunks. So it is really good because some embeddings models struggle to deal with some database where you have chunks of different sizes. But the main problem of this is that you may split connected information, and we really want to avoid this situation. The second method that I would really recommend if you can use it is the base structure splitting. So here we require that we were able to get the structure of the document during the parsing. It won't be always possible, but if you can keep the structure of your document during parsing, then you must, you don't must, but you should definitely try this method. The idea is that for using the structure, so I don't know, if you have some headers, every time I have a new headers, I will create a new chunk. It is really nice because you are minimizing the risk of splitting some connected information. But there is like this default of potentially you will have like a big variety of chunk size. That can be a problem for some embeddings model. I still really recommend this solution if you can. And the last one is semantic splitting. There it is more complex. It requires LLMs, but the idea is to regroup all the information using the semantic. You can give it a try, but please try first by the 2 other options. Now I will just show you a real example about this, the 2 first methods, so fixed length method and also the structure-based method. And yeah, it is like the extracted text we get from the PyPDF loader. So for the fixed length method, you can see that we have 4 chunks, probably the same size. One main problem is that on the first 3 chunks, we have the first paragraph of our document. So we really are splitting connected information. If you look at the second paragraph, all this information are related to our dog, but we never read the name of the dog. Now, if we look at the splitting, the structure-based method, you can see that there is one chunk for every header. So then we will not cut any information. We did not split any information, but we will have a real difference of size, of chunk size. So it is also a problem, a smaller problem, I would say. Now let's talk about encoding. So the most important part about RAG. Let's admit that we choose the fixed length method on our data. So we have the 4 chunks. We can compare these chunks to say, I want to use the second chunk to answer my question. It is not possible to do this with text. But we talk about embeddings model that are able to transform text into vectors using semantic. So that what we will do, and for every chunk, we will have a new vector. All of these vectors, we will put them in a vector store database. And now let's admit we have a question. So my question is, which languages can my dogs understand? First, we need to encode this user's question to compare it with all of the chunks we have in our vector database. And it's really, really important to use the same embeddings model that we use for the creation of the vector database. Or it won't work at all. And now we have a vector, and we can compare it to all the vector in our vector database. So for this, you need a similarity function, calculation function. For this example, I will use the squared Euclidean distance because it is the default one used by LangChain. But of course, you can choose the one that you prefer. Here are the results. So for every chunk in our database, we have a score. Because we use, as I said, the squared Euclidean distance, we are looking for the lower score. Here it's the second vector. The idea is that then we will select this vector for, we will consider that this is the most similar vector than our query, and then we will select it to answer our question. So let's have a look on what it is. Yeah, okay, sorry, I missed the slide. So here's what I have now, the query and the most similar chunk. If we look at the content of the query, it is which languages can my dog understand? And if we look at the content of my chunk, we have the sentence whether spoken in English, Spanish, or French. So in this example, it works. It won't work every time, of course. But yeah, that's a cool example about that show how RAG can handle some kind of situation. I would like, before letting Mascha talk, I would like to show you the code we needed to do this application. It's not that much. I mean, that's really, really small. And all of these are tools from LangChain. So you can do it really easily by your own and have like a RAG application that is running. On the lower, on the bottom left of the slide, you can see a link. You will be able to access to a repo with a notebook where you can access to this code and some explanation. So I really, if you are looking to do some RAG, I really recommend you to have a look on this and try by yourself. And I will let Mascha talk about how to include these RAGs into practical application.
Thank you very much, Victor, for this explanation. So the result of the explanation you just heard was more or less the core of RAG. In the following part, I will talk about how we can extend this core RAG service actually to an application which we can give to our users. For this, I will first address the main point behind building a custom RAG instead of using existing options, how to ensure the data privacy. Then I will move on towards how to expand and adapt a RAG to a custom workflow and use case. At the end, I will additionally give a short example of how we can use advanced techniques like prompt engineering to further optimize this RAG chain. So before I go to the actual explanations, let's first actually define what we understand from the RAG core. From the RAG chain that I previously showed, it's more or less the retrieval part and the in and outputs. So in the next few slides, it will always like be, there's the rec core. We expect that we read in a documents or the user query and then get the retrieved information chunks. Let's start now with getting a look at the data privacy. One of the most important decisions influencing data privacy is how to actually connect like the rec application with the necessary embedding model. Generally, we have like two strategies, self-hosting and API usage. While self-hosting definitely makes it very easy to control the data, it also needs a lot more investing into hardware and maintenance effort. So it is to note that we do see that especially like very efficient embedding models have a very high effort here and mostly actually need really high efficiency GPUs. And of course, there's like a new embedding model coming out every week. So there's also effort to keep up to date. The alternative, as said before, is like to use an API or service, like for example, what is offered by the OpenAI. Of course, here we have an out-of-box solution and really low effort, like it's 3 code lines to really integrate an API if it's like OpenAI. But on one hand, we do have to get effort into like researching what is their data privacy policy, what are the experiences, do they even keep their promises? And at the end, we have to be like really, really careful or cannot even like put in personal or sensitive data. An alternative, at least for like research and testing low throughput application, is the previously introduced Blablador. This service hosted as FCJ has the specialty that we do not train models, which means that user data will never become part of the AI answers. And additionally, after the user like closes their browser, the full message history is deleted, and as such, no user data is retained. It is to mention that Blablador is still an experimental service, and as such, for example, the available models can change. There may be not availability the whole day, and like there are not always capacities for high throughput use cases. After clearing the question of data privacy, let's actually look on how to build a framework around a rec core. Actually, with the existing Python packages, this is pretty easy. In this example, you can see screenshots from the Gradio package, which actually allows to get in to surround a lot of AI applications with a very simple interface. In the rec example, this could, for example, just mean taking a query, piping it to the rec core, and then displaying the one chunk with the highest similarity. And there already is a very, very basic testing or even user application. While this framework building is actually not very difficult, the greatest difficult actually lies in the pre- and post-processing steps when trying to integrate the rec core, for example, into a more complex application. The image you can see here compiles some possible pre- and post-processing strategies that can be built around a rec core to optimize the system to a specific framework and use case. Please note, this overview is neither complete nor actually displays the most efficient combination, just some that we in our research noticed. Now let's go over the displayed strategies and their effect on the rec shortly. In the pre-processing phase, on the left side, it is often beneficial to invest in a step we here call the query cleanup. This means nothing more than making sure that the query the user submitted is free of spelling and grammar errors and maybe even has got punctuation. In our experiences, this actually raises the accuracy of the retrieval process quite a bit. It could actually be also helpful, if you have a very specific domain, to try and transform the query into more of the domain wording. Maybe here it's even beneficial to say you keep the original query, a clean query and like a varied query to get more information if with the normal setup you do not really have the right answers. In the retrieval step, it is possible to actually not only query one store, but multiple stores. Here, for example, you can use stores built with different chunking strategies. As you saw before, the chunking strategy actually changes how the text is embedded very greatly. If you say you have a database that has very inhomogeneous data, like at some point you have like really well-structured PDFs, and then you have like, I don't know, very short and unspecific user feedback from somewhere, it might be very beneficial to try and apply different chunking strategies, then take a larger amount of possible relevant data, and in the next step, based on your own criteria, do something called re-ranking, where you more or less, for example, based on metadata, the actual contained information, try to resort like the priority of the different answers. This would be like one of the first steps done in the post-processing, and the result would be that you have a rather small amount of relevant information that fits in the context window of the LLM you use. Now, as said before, normally RAG applications continue into like a chatbot or LLM, and as such, the last step of post-processing is the augmentation of the query. Here you can, of course, choose to just take your query, make like a space, and then post your chunks. But this often, with many models, is not too efficient. So often, like techniques using prompt templates are applied. Here you more or less say like what kind of function the text has and some more details, but there's a little example at the end. Before that, I would like to mention the logical agents, but only very short. Like logical agents means that you mostly use like an LLM or even classic natural language processing to make decisions in this step. For example, you want to filter from your chatbot, is this relevant actually for the embedded data, or do I need to use word knowledge? You could ask the prompt, does the query relate to my data? And on the other hand, at the end, you could like verify that the answer generated by the LLM actually fits the data that was received by asking, did the data answer the query correctly? These were like strategies that you can build around the existing RAG core, but in a few specific use cases, that might not exactly be enough to get the accuracy you needed. Here, you can actually take a look at alternatives, like for example, the graph RAG. This alternative would be at the step of actually embedding and then driving the data into a vector store. For a short example for this graph RAG, if you like have if you have like the example text here, our tabby cat Luna is fully vaccinated, she is, and so on. In classical chunking, where you, for example, split sentence for sentence, you have the problem that the pronouns cannot be linked anymore to like the tabby cat Luna or the black cat Maui. You lose more or less the semantic coherency in the text. Graph RAG here has the special like logic that it tries to identify entities and then link the attributes to these entities. Here you could, for example, easily search which of those cats are chipped. Result, only Maui has been chipped. This way of encoding can be very helpful in diverse use cases where the focus is very heavily on the relation of the information and not so more as going to a very inhomogeneous database. So as said before, I would now like to show you a small example of how to enhance like the RAG chain using the technique called prompt engineering. Prompt engineering means nothing more than really thinking about how you ask in a large language model a question. For example, on the left side, a very simple example is shown. Like imagine that you have like a report from a project and you ask ChatGPT, where are we in the project, and then copy paste the report. And here is a real answer given by Llama 3 on this hypothetical report. It appears we are not currently working on a project together. Absolutely useless for our use case. This is most likely because our model doesn't really understand that the text it sees after the query is actually related to it and should be used. If we now wrap our query and the chunks into a template that, for example, says, answer the following user question using only the context below, and then really naming the text that comes, relevant context, we can see, like here on the right side, that we actually get a useful answer. It is prompt engineering is a very broad area that we definitely cannot cover in this talk. So please just take this as a keyword for further research if you are interested. So this was the part about integration, and now I would give over to my colleague Fritz for the takeaways and outro.
Yeah, thanks, Mascha, for those very nice insights. Yeah, so this won't take very long. Let's have a look at a summary of what we've heard and what could be your next steps to get started. Yeah, so this overview shall show you when it makes sense to take a look at RAG, also to manage your expectations, be realistic, what RAG cannot do, and how to start. So I think it was already clear or said multiple times in this presentation, if you have specific data, and I'm also thinking about like your research software artifacts could be one use case. If you have domain-specific data that somehow changes and you want accurate results, give it a try. I think RAG could be a good thing for you, especially it doesn't require training. So we're not talking about fine-tuning, it's just integrating data with low effort. But what RAG cannot do and cannot solve is what we also often see, expectations like somehow magically it will solve all your problems. But if data in the background is missing or incomplete or redundant with different kind of information, this is challenging. So it won't fix that. So this has to be clear. It doesn't understand the data, it retrieves and then takes what it has retrieved and generates an output. And lastly, it's not plug and play. So especially this part where Victor has talked about with the Sir Barks-a-lot example, that was meant to show that it's not plug and play based on the specifics of your data. And in your case, it could be some source code, for example. It's not plug and play. You have to spend time on data preparation and finding the best solution for your kind of data. However, we advise you start small, take one data source, one use case, and just try out. Because, as you've also seen in this minimal code example, coding-wise, it's not a lot. And we offer also off-the-shelf tools, and Langchain offers them. We in parts summarize them, and that leads me to the last slide here, with a call to action, explore our solutions. We will, I think Victor will post something in the chat. It was mentioned there's a Jupyter notebook where you could try it out yourself. We have also other resources which you can request after the talk. Make use of BlaBlaDor. I also saw this in the chat that it was appreciated already. Lastly, let's collaborate. We have consulting offers through our initiatives, Helmholtz AI and West AI. Also there should be some links in the chat, and we are very happy to get in contact. See if we can help with some consulting calls or even workshop formats. These are our key messages for takeaway. Now, quickly showing the sources. You've seen the nice image of the dog, and Langchain or Llama were mentioned, BlaBlaDor. And this is the final thank you slide.
Thank you for watching our seminar. Please check out the slides on Zenodo linked below, and see you next time.